Imagine a future so distant that humanity has already spread beyond the solar system. Cities glow beneath alien skies, orbiting distant stars. Entire civilizations communicate across light years as casually as we send messages today. And somewhere in that unimaginable age, a machine leaves the Milky Way for the very first time. A fragile metallic ambassador crossing the dark ocean between galaxies. Its name is Wanderlust 1. Built over centuries and carrying the collective knowledge of thousands of worlds, the probe moves silently toward Andromeda. Behind it, billions watch the live transmission. For humanity, this is more than exploration. It is proof that our species has finally escaped the gravity of its cosmic birthplace. The probe drifts beyond the final stars of the Milky Way. Ahead lies the intergalactic void, a region so empty that a human mind struggles to comprehend it. No suns, no planets, only darkness stretching for millions of light years in every direction. Then, something impossible happens. Without warning, the center of the spacecraft folds inward, not explodes, not collides, folds. The metal twists like paper dropped into a furnace. Entire sections vanish into nothingness. Antennae snap apart and disappear from the transmission feed. Within seconds, the probe tumbles lifelessly through the void. Its mission ends before humanity even understands what touched it. At first, scientists suspect sabotage or mechanical failure, but the damage makes no sense. No debris field appears. No radiation burst is detected. There is only distortion, as though space itself briefly cleansed down around the ship like a fist. Then the horrifying explanation emerges. Wanderlust 1 was struck by a black hole. Not a giant black hole lurking at the center of a galaxy. Not a stellar black hole born from a dying star. Something far stranger. A microscopic black hole. An invisible object, smaller than an atom, yet carrying the mass of an enormous animal. A relic older than stars themselves. A fragment left behind from the birth of the universe. A primordial black hole. For decades, objects like these belong mostly to theory. Exotic mathematical possibilities hiding in equations few people understood. Even many astrophysicists doubted they truly existed. Because according to everything we thought we knew, black holes were supposed to form only one way, through the violent deaths of massive stars. A star spends most of its life fighting against itself. Gravity constantly tries to crush it inward. Meanwhile, nuclear fusion in the core pushes outward with unimaginable force. For millions or billions of years, these two forces remain in balance. The star survives because the battle never ends. But eventually the fuel runs out. Fusion slows. The outward pressure weakens. And gravity, patient as ever, finally wins. For the largest stars in the cosmos, the collapse becomes catastrophic. The core implodes faster and faster until matter is compressed beyond comprehension. Atoms themselves are destroyed. Electrons and protons merge together. Space around the dying star begins to deform. Then comes the supernova, an explosion so powerful it can briefly outshine entire galaxies. Outer layers are hurled into space at enormous speed while the crushed core continues collapsing inward. And if enough mass remains, nothing can stop the process. Not pressure, not energy, not even the laws governing ordinary matter. Eventually, the collapsing core crosses a boundary called the Schwarzschild radius. At that point, escape becomes impossible. To leave would require moving faster than light itself. And because nothing can exceed light speed, the object vanishes behind an invisible horizon forever. A black hole is born. For much of modern science, this was considered the only realistic path to creating one. Black holes were thought to be the corpses of giant stars. That idea seemed reasonable because the physics involved are extreme beyond imagination. To create a black hole, matter must become absurdly dense, far denser than anything humans encounter in daily life. A teaspoon of neutron star material would outweigh Mount Everest. Yet, Even neutron stars are not dense enough to become black holes. Something even more violent is required. Gravity must compress matter so completely that all known forces fail to resist it. The universe does not permit such conditions easily, and this created a problem, because astronomers eventually discovered black holes far larger than they should have been. Monsters weighing millions or even billions of times more than our Sunday. Objects so massive they sat at the centers of galaxies like cosmic engines. Supermassive black holes. By the late 20th century, scientists realized that nearly every large galaxy seemed to contain one, including our own Milky Way. Hidden deep within the galactic center lies Sagittarius A gravitational giant around 4 million times the mass of the Sunday. Stars orbit it at terrifying speeds. Entire solar systems dance around its invisible pull. At first, researchers assumed these giant black holes simply grew over time. Perhaps smaller stellar black holes consumed enough matter to become enormous. But the more we observed the universe, the stranger the situation became. The earliest galaxies already seemed to contain gigantic black holes, and that should have been impossible. Light from distant galaxies is also light from the past. Because space is so vast, telescopes effectively function as time machines. When astronomers observe galaxies billions of light years away, they see them as they existed billions of years ago. They see ancient cosmic history unfolding in real time. And what they found was deeply unsettling. Young galaxies in the infant universe already possessed mature supermassive black holes. Some existed only a few 100 million years after the Big Bang itself. There simply had not been enough time for ordinary stellar black holes to grow that large. Not according to conventional physics. Then came the James Webb Space Telescope, a machine capable of peering deeper into cosmic history than any instrument before it. When Webb began transmitting data back to Earth, astronomers expected surprises. But few were prepared for what appeared in those first observations. Tiny ancient galaxies containing impossibly massive black holes. Some of these black holes existed when the universe was less than 5% of its current age. To create them through normal growth would require feeding at absurd speeds continuously for hundreds of millions of years. Even then, many calculations still failed to work. It was as though the universe had somehow cheated. As though giant black holes appeared before stars had enough time to build them. And that possibility changes everything, because if black holes did not always need stars to form, then entirely new origins become possible. Origins tied not to dying suns, but to the birth of the cosmos itself. A time when the universe was hotter, denser, and more violent than anything that exists today. A time when reality behaved in ways we are only beginning to understand. To understand primordial black holes, we must travel backward beyond galaxies, beyond stars, beyond even atoms themselves. Back to a universe so young that time had barely begun to move forward. A cosmos compressed into a state almost impossible for the human mind to visualize. No planets existed there. No light in the way we understand it today. In the first moments after the Big Bang, the universe was not empty space expanding outward into darkness. It was everything at once. Matter, energy, radiation, and space-time itself existed as a single violently expanding ocean of unimaginable heat. Temperatures exceeded trillions upon trillions of degrees. Physics operated under conditions no laboratory on Earth could ever recreate. At that stage, the universe was smaller than an atom. Yet inside that tiny volume existed all the mass that would eventually become galaxies, stars, oceans, mountains, and people. Every black hole that would ever exist was encoded into those first chaotic moments. The entire cosmic future was compressed into a storm of raw possibility, and hidden within that storm may have been the seeds of something terrifying. Modern cosmology often describes the early universe as smooth and uniform, but in reality, it was never perfectly even. Tiny fluctuations existed everywhere. Regions where matter density was slightly higher sat beside regions where it was slightly lower. These imperfections were microscopic, but they changed the fate of the cosmos forever. Today we can still see traces of those ancient fluctuations. They appear in the cosmic microwave background, the oldest light in the universe. Satellite missions like COBE, WMAP, and Planck mapped these ancient temperature variations with astonishing precision. Small differences in density eventually became galaxies and galaxy clusters. Without those imperfections, stars might never have formed at all. But some physicists believe a few fluctuations were far more extreme than the others. Not merely dense enough to create galaxies, dense enough to collapse instantly under their own gravity. Dense enough to bypass the formation of stars entirely. Dense enough to become black holes almost immediately after the birth of time. These would not be stellar black holes. No supernova would create them. No collapsing star would precede them. It would emerge directly from primordial energy itself. Black holes born before the first star ever ignited. And unlike ordinary black holes, primordial black holes could exist across an enormous range of masses. Some may have been gigantic from the beginning. Others may have been astonishingly tiny. A mountain compressed smaller than a grain of sand. An asteroid's mass trapped inside a space smaller than a proton. This idea sounds absurd at first. After all, black holes are usually imagined as giant cosmic monsters devouring stars. But the size of a black hole is not determined by how dangerous it is. Its true power comes from density, and density can become extreme on unbelievably small scales. If Earth were compressed into a black hole, it would shrink to roughly the size of a marble. The sun would become a sphere only a few kilometers wide. A human being transformed into a black hole would be smaller than an atomic nucleus. The smaller the black hole, the more unnatural it begins to seem. Matter itself appears to lose meaning under such conditions. Yet according to Einstein's equations, the mathematics allows it. Gravity does not care whether the collapsing object is a star or a microscopic region of dense primordial plasma. If enough mass enters a sufficiently tiny volume, collapse becomes inevitable. Space-time caves inward. An event horizon forms. For decades, primordial black holes remained an obscure theoretical curiosity. Interesting mathematics, but unsupported by evidence. Many scientists considered them unlikely because no mechanism clearly explained how enough density could gather in one place. Others argued that even if they formed, they would not survive until today. And that objection came from one of the greatest physicists in history. In 1974, Stephen Hawking made a revolutionary discovery. Black holes, according to quantum mechanics, are not completely black. They slowly emit tiny amounts of radiation. This process became known as Hawking radiation, and its implications were extraordinary. Quantum theory tells us that empty space is never truly empty. Even a vacuum seethes with temporary particles constantly appearing and disappearing. Near the edge of a black hole, these quantum fluctuations behave strangely. One particle can fall inward while the other escapes into space. To an outside observer, it appears as though the black hole is emitting radiation. Over immense stretches of time, this causes the black hole to lose energy. And because energy and mass are connected, the black hole gradually shrinks. A massive black hole evaporates incredibly slowly, far slower than the current age of the universe. But tiny black holes would evaporate much faster. This became a major problem for primordial black hole theories. According to Hawking's calculations, the smallest primordial black holes should already be gone. After billions of years, they would have radiated themselves completely out of existence. No black hole rhinos. No microscopic relics drifting through interstellar space. For many years, this seemed to settle the issue. Primordial black holes remained mathematically possible but physically irrelevant. Interesting concepts hiding inside equations. Nothing more. Then, astronomy entered a new era. As telescopes improved, scientists began discovering black holes that seemed impossible to explain conventionally. Quasars powered by enormous black holes appeared shockingly early in cosmic history. Some existed when the universe was younger than expected galaxy formation models allowed. Again and again, observations contradicted theoretical timelines. Something fundamental appeared to be missing from our understanding. The James Webb Space Telescope intensified the mystery dramatically. Its infrared instruments peered into the deep, ancient universe with unprecedented clarity, and what Webb found disturbed astronomers around the world. Galaxies were appearing too early. Black holes were growing too fast. Some ancient galaxies seemed strangely mature, despite existing close to the dawn of cosmic history. Heavy structures had formed far sooner than expected, and at the centers of many of these systems sat black holes already millions of times heavier than the Sunday. The timeline simply did not fit standard models. The universe looked older than it should have been. Then came one of the strangest discoveries of all. Astronomers observed a supermassive black hole apparently existing between galaxies rather than inside one. It was not sitting at the center of a stellar system as expected. Instead, it appeared isolated within a collision zone between galaxies, a cosmic orphan with no obvious origin. Researchers proposed that it may have formed directly from the collapse of a massive gas cloud, not from a star, not through slow accumulation over billions of years, but through direct collapse under extreme conditions, an echo of primordial black hole formation mechanisms. Around the same time, scientists examined ancient galaxies containing surprisingly low amounts of heavy elements. This mattered enormously. Stars manufacture heavy elements over generations of fusion and supernova explosions. A chemically primitive galaxy suggests very little stellar evolution has occurred. Yet some of these primitive galaxies already hosted enormous black holes. The implication was deeply unsettling. Perhaps some black holes came first. Perhaps galaxies formed around black holes instead of the other way around. Perhaps primordial black holes acted as gravitational seeds that helped organize the early universe itself. And, if that is true, then the universe may still contain their smaller cousins. Tiny primordial black holes hiding in darkness. Invisible relics from the first second of existence. Objects so dense and compact that detecting them becomes almost impossible. Ancient survivors drifting silently through the Milky Way even now, and humanity may have absolutely no idea where they are. By the early 21st century, astronomy faced an embarrassing problem. The universe did not behave the way it was supposed to. Galaxies spun too quickly. Clusters of galaxies held together when they should have flown apart. And gravity across the cosmos appeared far stronger than visible matter alone could explain. According to everything scientists could observe, there simply was not enough mass in the universe. At least not enough ordinary matter. Stars, planets, gas clouds, nebulae, and black holes together accounted for only a small fraction of the gravitational effects astronomers measured. Something unseen was shaping the cosmos on gigantic scales. Something invisible surrounded galaxies like a hidden skeleton. Scientists named this mystery dark matter. Not because it was literally dark, but because nobody knew what it was. It emitted no light. It absorbed no light. It barely seemed to interact with ordinary matter at all. Yet its gravitational influence was undeniable. Without dark matter, galaxies should not exist in their current form. The Milky Way itself rotates too rapidly to remain stable based only on visible mass. Something extra is holding everything together. Something enormous surrounds us right now. Modern estimates suggest ordinary matter makes up less than 5% of the universe. Dark matter appears to account for roughly 27%. The rest belongs to the even stranger phenomenon known as dark energy. In other words, almost everything in existence is fundamentally unknown to us. Humanity understands only a tiny fraction of reality. For decades, physicists proposed exotic particles as candidates for dark matter. WIMPs, axions, sterile neutrinos, and entirely new forms of matter emerged from theoretical models. Huge underground detectors were built to search for them. Particle accelerators attempted to create them artificially. But despite decades of effort, nothing definitive appeared. The deeper scientists searched, the stranger the silence became. Dark matter was everywhere gravitationally, yet nowhere directly detectable. It behaved less like ordinary matter, and more like a hidden framework woven through space-time itself. And eventually, some researchers revisited an old, forgotten possibility. What if dark matter was not matter at all? What if at least part of it consisted of black holes? Not giant black holes. Those would distort galaxies too violently and reveal themselves through gravitational lensing. Astronomers would see stars bending unnaturally behind them. Large black holes could not hide easily, but tiny primordial black holes were different. A black hole smaller than an atom emits no light. Without surrounding gas to consume, it becomes almost completely invisible. It drifts silently through space, detectable only through gravity. And on microscopic scales, those gravitational effects become extraordinarily difficult to observe. This idea transformed primordial black holes from theoretical curiosities into possible cosmological suspects. Perhaps the universe was not filled with exotic particles at all. Perhaps dark matter was a vast swarm of ancient microscopic black holes, invisible relics from the Big Bang itself, an ocean of hidden gravity surrounding every galaxy. Imagine the Milky Way not as empty space between stars, but as a minefield. Millions upon millions of microscopic black holes drifting through darkness. Most would be harmless due to their tiny interaction cross-sections, but every so often, one might pass dangerously close to ordinary matter, and the consequences could be catastrophic. A primordial black hole with the mass of a rhinoceros would be unimaginably tiny, far smaller than an atom. Yet its gravity near the event horizon would be extreme beyond comprehension. If such an object passed through a human body, the damage would be microscopic but devastating. Matter along its path would experience violent tidal forces instantly. Thankfully, collisions on human scales would likely be extraordinarily rare. Space is unimaginably vast. Even if millions of primordial black holes exist inside our galaxy, they would still be separated by enormous distances. Most would wander forever without touching anything significant. But rare does not mean impossible. Some scientists began wondering whether tiny, unexplained cosmic events could actually involve primordial black holes. Brief gravitational anomalies, unusual microlensing observations, mysterious flashes of radiation, subtle distortions in stellar motion. Microlensing became especially important. Einstein's theory of relativity predicts that massive objects bend light around them. A black hole passing between Earth and a distant star can briefly magnify the star's light like a lens. Astronomers use this effect to search for hidden objects in space. And occasionally, strange events appear without clear explanations. Most turn out to involve ordinary stars or planets, but not all observations fit neatly into existing models. A few researchers argue that certain microlensing events may hint at populations of compact invisible objects wandering the galaxy, possibly primordial black holes, though the evidence remains highly controversial. The challenge is scale. A microscopic primordial black hole would not behave like the giant black holes shown in science fiction films. It would not swallow stars whole. It would not drag planets into spirals of doom from millions of kilometers away. Its danger comes from concentration, not size. If one passed through Earth, it might travel straight through the planet almost unnoticed. Yet, along its path, matter would experience intense compression and heating. Some theoretical models suggest it could trigger localized seismic disturbances. Others predict almost no measurable effects at all. The uncertainty itself is unsettling, because nobody has ever observed one directly. Everything about primordial black holes exists at the edge of theory and inference. Scientists are attempting to reconstruct invisible objects from tiny disturbances in cosmic behavior. It is like trying to identify a shark by studying ripples in black water at midnight. The conclusions remain uncertain. Then, in 2024, a controversial study reignited the debate dramatically. Researchers suggested that Hawking radiation might weaken at extremely tiny scales. Instead of evaporating completely, microscopic black holes could stabilize into long-lived remnants. The evaporation process might slow almost to a halt near the end, leaving behind permanent ultra-small black holes. If true, the implications are staggering. Primordial black holes, smaller than atoms, may still exist all around us. Not dead remnants from the early universe, but surviving ancient objects older than every galaxy. Invisible fossils from the birth of space-time itself, and potentially abundant throughout the cosmos. This possibility changes the emotional character of the universe entirely. Space no longer feels merely empty. It becomes populated by hidden gravitational predators too small to see. Darkness itself begins carrying weight. The vacuum becomes alive with invisible danger. And yet, there is another unsettling implication. If primordial black holes survived, they may not only explain dark matter, they may also explain the rapid formation of galaxies, quasars, and supermassive black holes. Tiny primordial seeds could have merged over billions of years into the cosmic giants we observe today. The largest structures in existence may have begun as microscopic imperfections in the first second of time. That idea creates a terrifying symmetry. The smallest black holes may have built the largest structures in the universe. Galaxy clusters, quasars, and perhaps entire cosmic filaments may owe their existence to primordial gravity wells formed before stars existed. The architecture of the observable universe may have emerged from microscopic chaos. Reality itself may have grown from invisible singularities. And if that is true, humanity's picture of cosmic history is incomplete in a profound way, because the universe we see today may not primarily be shaped by stars. It may be shaped by hidden black holes we still cannot detect directly, ancient objects drifting silently through interstellar darkness, waiting for us to finally notice they were there all along. Human beings evolved to fear visible threats. Predators with teeth, storms gathering on the horizon, fire rising from forests. But primordial black holes belong to a category of danger the human brain was never designed to comprehend. You cannot see them approaching. You cannot hear them. No alarm system would warn you in advance. A primordial black hole drifting through the solar system would be darker than empty space itself, an invisible object carrying the density of collapsed reality. Fortunately, most scientists believe the odds of a direct encounter are extremely small. Even if primordial black holes exist in large numbers, the galaxy remains mostly empty. The distances between objects in space are enormous, beyond intuition. Stars themselves rarely collide. Entire galaxies can pass through each other with relatively little direct impact. But unlikely is not the same as impossible. And physics becomes deeply disturbing once we explore what such an encounter would actually look like. Because unlike ordinary asteroids or comets, primordial black holes do not damage objects through collision alone. Their true weapon is gravity concentrated into microscopic space, and concentrated gravity behaves monstrously. Imagine an object no larger than a proton entering Earth's atmosphere. There would be no fiery trail, no sonic boom, no visible descent through the sky. It would pass through air molecules almost effortlessly. But around that microscopic point exists an extreme gravitational gradient. Anything passing too close experiences tidal forces unlike anything on Earth. Matter nearest the black hole accelerates faster than matter slightly farther away. The result is stretching, compression, and violent deformation on atomic scales. Space itself becomes distorted around the object's path. If a primordial black hole passed through your body, the event might occur faster than nerve signals could travel. A tiny channel of catastrophic disruption would form along its trajectory. Atoms would be compressed and heated violently. Cells would rupture instantly. The damage would be microscopic but lethal. Now scale that upward. What if one passed through a spacecraft? Or a nuclear reactor? Or a densely populated city? The black hole itself might continue onward almost unaffected, but the gravitational interaction could unleash localized destruction, difficult to predict. Some theoretical studies suggest that extremely tiny primordial black holes might produce little noticeable effect while crossing Earth. Others predict seismic disturbances, bursts of radiation, or strange localized heating events. The uncertainty exists because we are operating far beyond experimental physics. Humanity has never studied a primordial black hole directly. Every scenario remains partly speculative. Yet the danger becomes far more severe as mass increases. A larger primordial black hole could gravitationally capture surrounding matter more efficiently. As it consumes mass, it grows stronger. Its interaction with Earth could become increasingly destructive over time. In extreme cases, catastrophic planetary consequences become possible. Fortunately, there is currently no evidence that such massive primordial black holes are common near Earth. If they were abundant, astronomers believe we would already observe unmistakable gravitational signatures. Planetary orbits would behave strangely. Stars would wobble unpredictably. Galactic dynamics would reveal their presence. Still, the smaller variants remain difficult to rule out, and that uncertainty creates a uniquely modern kind of fear. Not fear of invasion or war. Fear that invisible relics from the birth of the universe may already surround us unnoticed. Ancient objects moving silently through the dark. What makes primordial black holes especially unsettling is that they blur the boundary between particle physics and cosmology. They are both microscopic and astronomical simultaneously. Quantum mechanics governs their evaporation. General relativity governs their gravity. They exist at the crossroads of physics itself. That intersection matters enormously, because modern science remains incomplete. Einstein's relativity explains gravity beautifully on large scales. Quantum mechanics explains the microscopic world with astonishing accuracy, but the two frameworks resist unification. At singularities like black holes, our equations begin to fail. Inside a black hole, physics encounters a wall. Density approaches infinity. Space-time curvature becomes mathematically undefined. Known laws collapse into contradiction. Nature hides something fundamental behind the event horizon. Primordial black holes may therefore contain clues to the deepest unanswered questions in science. Questions about quantum gravity. Questions about the structure of space-time itself. Questions about whether singularities truly exist physically or merely reflect incomplete mathematics. Tiny black holes may hold enormous secrets. Some theories become even stranger. Certain physicists have proposed that microscopic black holes might connect to extra dimensions hidden beyond ordinary perception. Others suggest they could encode information about the earliest inflationary moments after the Big Bang. A few radical models even hint that black holes could generate entirely new universes internally. Reality becomes profoundly bizarre near singularities, and this leads to an uncomfortable possibility. Perhaps primordial black holes are not merely cosmic debris. Perhaps they are fundamental building blocks of structure throughout the universe, the hidden scaffolding beneath galaxies, the invisible architecture behind cosmic evolution itself. If so, then humanity's place in the cosmos changes dramatically. We are no longer inhabitants of a mostly empty universe sprinkled with stars. We become creatures moving unknowingly through an ocean of invisible gravitational relics. Ancient objects older than galaxies passing silently through the Milky Way around us. The darkness becomes populated. This realization also changes how we imagine future exploration. Science fiction often portrays interstellar travel as a challenge of distance and energy. But what if the void between stars contains hidden hazards impossible to detect easily? Microscopic singularities drifting through interstellar space at enormous speeds. Invisible bullets forged in the first second of existence. A spacecraft traveling near light speed would face unimaginable vulnerability. Even collisions with dust grains become dangerous at relativistic velocities. Now imagine encountering an object carrying the mass of a mountain compressed beneath an event horizon smaller than an atom. No shield technology currently imaginable could reliably defend against such a collision. The encounter would occur instantly. This is why some physicists describe primordial black holes as cosmic landmines. Rare, perhaps, but potentially catastrophic. And unlike asteroids or radiation storms, they may be almost impossible to predict in advance. A civilization could travel safely for centuries before disaster strikes without warning. Yet, despite these fears, primordial black holes also represent scientific opportunity. If humanity could detect one nearby, it would revolutionize physics overnight. Observing Hawking radiation directly would transform quantum theory. Studying microscopic event horizons could reveal entirely new laws of nature. The discovery would rank among the greatest moments in scientific history. Several observatories are already searching indirectly for signs of these objects. Astronomers monitor stars for strange microlensing events. Particle detectors search for unusual radiation bursts. Gravitational wave observatories listen for tiny mergers hidden inside cosmic noise. So far, nothing conclusive has emerged, but absence of evidence is not evidence of absence. The universe has repeatedly humbled humanity throughout history. Again and again, reality proved stranger than expected. Galaxies beyond the Milky Way, black holes themselves. Even dark matter once sounded absurd. So did gravitational waves. So did planets orbiting other stars. Each discovery forced humanity to redraw its understanding of existence. Primordial black holes may become the next revision. And perhaps the most unsettling part is this. If primordial black holes truly exist, then some of them may have wandered the cosmos untouched since the dawn of time. Before Earth formed, before the sun ignited, before atoms stabilized into matter as we know it. Ancient survivors, from the birth of reality itself, still drifting through darkness after 13.8 billion years. Silent, invisible, eternal. And somewhere out there tonight, one may already be moving toward us through the stars. For most of human history, black holes represented finality, a one-way journey into oblivion. Matter falls inward, information disappears, and eventually, everything ends inside darkness beyond recovery. But modern physics has slowly begun dismantling that picture. Because the deeper scientists investigate black holes, the less they resemble simple cosmic vacuum cleaners. Instead, they begin to look like cracks in reality itself. Places where our understanding of existence breaks apart. Places where entirely new physics may emerge. At the center of this mystery lies a question that has haunted theoretical physics for decades. What happens when a black hole dies? Not a giant supermassive black hole, which may survive for timescales beyond imagination, but a tiny primordial black hole, a microscopic singularity slowly evaporating through Hawking radiation. According to classical calculations, the process ends violently. As the black hole loses mass, its temperature rises. The smaller it becomes, the faster it radiates energy away. Eventually, the evaporation accelerates catastrophically. The black hole explodes in a final burst of radiation. If this picture is correct, then the early universe may once have been filled with countless tiny black holes constantly dying in flashes of energy. Some physicists even searched for evidence of these ancient explosions. Gamma-ray observatories scan the sky looking for signatures of evaporating primordial black holes. So far, nothing definitive has appeared, but the search continues. Then came an even deeper problem, the information paradox. A crisis so severe, it threatens the foundations of physics itself, because according to quantum mechanics, information cannot truly be destroyed. The universe may transform information, but it cannot erase it completely. Black holes appear to violate that rule. Throw an object into a black hole, and its detailed information seems lost forever. Only the black hole's mass, spin, and charge remain observable externally. Everything else disappears behind the event horizon, at least according to classical relativity. But quantum theory refuses to accept this outcome. If information can vanish completely, quantum mechanics itself begins to unravel. Cause and effect become unstable. Predictability collapses. The laws governing reality stop making sense. This conflict triggered one of the greatest intellectual battles in modern science. Stephen Hawking initially argued that black holes truly destroy information. Others insisted this was impossible. For decades, some of the world's greatest physicists wrestled with the paradox. And the debate fundamentally changed how we think about black holes today. Many scientists suspect information somehow escapes. Not in obvious form, but encoded subtly within Hawking radiation itself. Others propose that information remains smeared across the event horizon like a holographic imprint. Some theories suggest black holes are less like prisons and more like ultra-compressed storage systems. Reality becomes increasingly surreal, near singularities. Primordial black holes make this mystery even stranger. Because unlike giant black holes hidden inside galaxies, tiny primordial black holes operate near the boundary where quantum mechanics dominates gravity. They are laboratories of impossible physics, natural experiments created by the Big Bang itself. Microscopic intersections between relativity and quantum theory, and this is where speculation becomes extraordinary. Some physicists now wonder whether singularities truly exist at all. Perhaps infinite density is not physically real. Perhaps our equations simply break down before reaching that point. Nature may hide a deeper structure beneath the mathematics. One possibility involves quantum gravity, a hypothetical framework uniting Einstein's relativity with quantum mechanics into a single coherent theory. Humanity has searched for this unification for generations. String theory attempts one solution. Loop quantum gravity proposes another. In certain quantum gravity models, black holes never form true singularities. Instead, collapsing matter reaches an extreme quantum state that prevents infinite compression. The black hole becomes a strange, exotic object with hidden internal structure, a gravitational corpse suspended between collapse and stability, something stranger than any classical black hole. Other theories become even more radical. Some researchers propose that evaporating black holes may leave behind stable remnants, tiny, ultra-dense objects incapable of shrinking further, permanent leftovers from incomplete evaporation, frozen singularities surviving indefinitely. If those remnants exist, they solve multiple problems simultaneously. Information would not be destroyed. Tiny primordial black holes could still survive today. Dark matter suddenly gains a compelling candidate, and Hawking radiation no longer leads to complete annihilation. But the implications grow stranger still, because some cosmologists suggest black holes may connect directly to the creation of universes themselves. Inside an event horizon, space-time becomes radically distorted. Time and space exchange roles, mathematically. Known geometry breaks apart completely. Certain speculative models propose that every black hole may contain an expanding internal space-time region. In other words, a universe, our own universe, might itself exist inside a black hole formed elsewhere. The Big Bang could represent the interior birth of a collapsing parent cosmos. Reality turns recursive. This sounds like science fiction, yet versions of these ideas appear in serious theoretical research. Not because physicists enjoy fantasy, but because existing equations keep pointing toward deeply counterintuitive conclusions. Black holes repeatedly force science beyond ordinary intuition. Every attempt to simplify them fails. They become stranger the closer we look. And primordial black holes may preserve traces of the earliest cosmic conditions better than anything else in existence. Stars evolve, galaxies collide, planets form and die. But a primordial black hole may remain fundamentally unchanged for billions of years. Imagine touching an object older than every galaxy in the sky, an artifact from the first second after time began, a relic that witnessed the birth of space-time itself. That is what a primordial black hole may be, a fossil from the dawn of existence. This is why the search matters so deeply. Finding primordial black holes would not merely confirm another astrophysical object. It would reshape cosmology, particle physics, gravity, and quantum theory simultaneously. Entire textbooks would require rewriting. Humanity's understanding of reality would transform overnight. And perhaps the most unsettling possibility is that the universe may already be filled with them, not just a few scattered remnants, but countless microscopic black holes drifting invisibly through every galaxy, a hidden ecosystem of primordial gravity, an unseen layer of cosmic structure beneath ordinary matter. If that picture is true, then humanity has misunderstood the universe at the most fundamental level. Space is not mostly empty. Darkness is not absence. The vacuum itself may be crowded with invisible singularities left behind by creation itself, ancient objects silently shaping reality from the shadows. And somewhere in that darkness, beyond the reach of our instruments, primordial black holes may still be colliding, merging, evaporating, and wandering between stars tonight. Invisible architects of cosmic evolution, ghosts from the beginning of time, waiting for humanity to finally realize that the universe was never empty at all. For thousands of years, humanity looked into the night sky and saw emptiness between the stars. Ancient civilizations imagined the heavens as scattered islands of light floating in a silent void. Even after modern astronomy transformed our understanding of the cosmos, that basic emotional picture remained. Stars here, darkness there. Matter separated by vast oceans of nothingness. But science has slowly revealed a more disturbing reality. The universe is not empty. It only appears empty because most of what exists cannot be seen. Invisible gravity shapes galaxies. Invisible radiation floods space. And perhaps invisible black holes drift silently through the dark even now. Not giant monsters consuming suns. Not cinematic whirlpools swallowing spacecraft whole. But microscopic singularities older than stars themselves. Ancient remnants born in the first heartbeat of existence. If primordial black holes are real, then they are among the oldest objects in the universe. Older than the Milky Way. Older than Earth. Possibly older than atoms in their current stable forms. They may have formed before the cosmos even became transparent to light. Think about what that truly means. Somewhere beyond our solar system may drift an object that has wandered untouched through cosmic history for 13.8 billion years. It survived the birth of galaxies. It survived stellar explosions, collisions, and the expansion of space-time itself. A perfect relic from the beginning of time. Human civilization feels ancient to us. Recorded history stretches back several thousand years. The pyramids already seem impossibly old. Dinosaurs ruled Earth for millions of years before vanishing into extinction. Yet against primordial black holes, all of human history disappears instantly into insignificance. Even the sun is temporary. In roughly 5 billion years, it will exhaust its hydrogen fuel and begin dying. Earth's oceans will evaporate. The inner solar system will transform into a furnace. Eventually, our star itself will become a white dwarf drifting through darkness. But some primordial black holes may still exist long after that. Long after galaxies collide and reshape the local cosmos. Long after stars stop forming entirely. Long after ordinary matter grows cold and scattered. The tiniest black holes may outlive almost everything else in existence. This creates a strange inversion in our understanding of permanence. We imagine black holes as destroyers, as endings. Yet primordial black holes may ultimately prove more enduring than stars, planets, or civilizations. Tiny islands of trapped gravity surviving while the universe itself ages toward darkness. And that darkness is coming. Modern cosmology predicts a distant future in which galaxies drift apart faster and faster due to cosmic expansion. Stars gradually burn out. The universe becomes colder, emptier, and quieter across unimaginable timescales. Eventually, even black holes themselves may begin to dominate cosmic history. In that far future, primordial black holes could become some of the last surviving structures in existence. Tiny remnants scattered through a dying cosmos. The final fossils of creation itself, objects carrying memories of a universe long vanished, silent witnesses to cosmic extinction. Yet perhaps the strangest realization is not their age or their danger, It is what they reveal about reality itself. Because primordial black holes expose how incomplete human understanding still is. We stand at the edge of enormous mysteries, and the universe keeps growing stranger the deeper we look. A century ago, black holes were considered mathematical absurdities. Many scientists doubted they could physically exist. Today, we photograph them. We detect gravitational waves from their collisions. We know they shape galaxies across the cosmos. Dark matter followed a similar path. At first, it seemed like an accounting error, a problem with calculations. Now it appears to dominate the gravitational structure of the universe. Yet, we still do not know what it actually is. Primordial black holes may become the next great transformation. Right now, they remain hypothetical, possible, unconfirmed, balanced between theory and evidence. But history repeatedly warns us not to underestimate nature's imagination. Reality has consistently proven more bizarre than human intuition allows. Quantum entanglement sounds impossible. Time dilation feels unreal. The idea that mass bends space-time itself once seemed absurd, yet all are experimentally true. Perhaps primordial black holes belong in that category as well. Objects so strange that the human mind instinctively rejects them. Microscopic singularities, wandering through galaxies unseen. Invisible gravity wells formed before stars existed. Relics from the birth of space-time itself. And if humanity eventually confirms their existence, the emotional meaning of the night sky may change forever. The darkness between stars will no longer feel empty. Every region of space may conceal hidden ancient objects drifting silently through the void. The cosmos becomes populated by invisible history. The vacuum itself acquires weight and memory. Future generations may one day map primordial black holes the way we map stars today. Spacecraft may learn to avoid regions dense with invisible singularities. Civilizations might even harness tiny black holes as power sources or propulsion systems. Physics that currently feels impossible may eventually become engineering. The history of science repeatedly follows this pattern. But there is another possibility, a darker one. Perhaps primordial black holes are not merely passive remnants. Perhaps they actively shaped the universe from the very beginning. Perhaps galaxies themselves formed around ancient black hole seeds. If so, then everything we see tonight may owe its existence to primordial gravity. The Milky Way, the stars overhead, the atoms in your body, all of it emerging from tiny density fluctuations moments after the Big Bang. That idea carries an almost philosophical weight. The largest structures in existence, born from microscopic imperfections in the infant universe. Chaos, becoming order across billions of years. Invisible singularities, sculpting cosmic architecture in silence. Creation emerging from fluctuations in primordial darkness. And somewhere out there tonight, beyond human sight, one of those ancient objects may still be drifting between the stars. A microscopic black hole, older than galaxies. Silent, invisible, carrying the gravity of collapsed space-time through the darkness of eternity. A survivor from the first second of existence. Perhaps it will wander forever, unnoticed. Perhaps one day humanity will finally detect one passing through the solar system. Or perhaps, centuries from now, a spacecraft crossing the gulf between galaxies will encounter one directly. An invisible relic waiting silently in the void. A reminder that the universe was never empty at all.